Hello students, we are today here to discuss about the fifth unit, that is the carbon chemistry, where we will discuss about the homolytic and heterolytic cleavages and the kind of reaction intermediates that are formed during the homolytic and heterolytic cleavages, such as carbocations, carbanions, carbon radicals, and the carbons. What is their general structure, hybridization. Then we'll move towards the electrophilic and nucleophilic behaviors, their stability, generation, and kind of reactions they undergo. Thereafter, we will have a general discussion about the reaction kinetics, which we will discuss through transition state theory, and we will have a revision about the rate constant, this free energy activation, as we have discussed in the transition state theory, while we have discussed the unit first, that was about the chemical kinetics, and then we will discuss the reaction profile diagrams for one-step and two-step reaction processes. Then we will go for substitution nucleophilic reactions, where we will discuss SN1, SN2, SNI reactions, then effect of substrate nucleophiles and the medium on the reactivity and the mechanism. Thereafter, we will discuss about the neighboring group participations, and then we will move towards elimination reactions, where we will go for E1, E2, and E1 CB mechanisms. And finally, we will discuss about the Sedgwick rule and the Hoffman rules, and then the comparison between elimination and substitution reaction for the particular substrates or the reactants. Now, moving ahead, first let's just start with this carbon chemistry. Carbon chemistry, it is so important that entire branch of chemistry that is devoted to this specific elements chemistry. And that is called as the organic chemistry, because organic chemistry is also defined as the branch of chemistry which deals with the compounds of carbon. Now, the number of carbon compounds, that is very high. And that is the reason why this is studied in a great extent and has a various subdivisions in the organic chemistry itself with respect to the carbon chemistry. First of all, I would like to make it very clear that is the general mistake that is shown by the students. Whenever you are going to discuss the organic chemistry or any bond, where you are going to detail about the or explain about the mechanism of the reaction, then you show the arrow to explain the mechanism where the cleavage of bond is occurring. And this arrow, its direction should always be in the direction of flow of the electron, not in the direction in which a particular cation or anion or radical is moving. It is always to be shown in the direction of flow of the electron. So this is a shared period of electron. This is moving towards oxygen. So the arrow, it should move towards, it should direct towards the oxygen atom. So we are having two examples over here. This hydroxyl ion and HCl, they are reacting over here. This proton, it is getting connected to OH, is getting bonded to OH. So it should not that hydrogen, it should be directed towards this lone pair on the oxygen atom through an arrow. Rather, electron, which is present on the electron, and this pair of electron which is present on the oxygen of the hydroxyl group, that should move towards the hydrogen atom. So the correct direction of arrow is in second case. It is in the second case, not in the first case. Why? Because here the direction is in the direction of movement of this hydrogen atom. Rather, it should ideally be in the direction in which this electron it is flowing. So this is the correct way to show the direction of arrow. So this arrow notation, it should be taken care whenever we are going to explain about the mechanism of any reaction. Okay. Now, as already we know that when a bond is cleaved, it can be fissioned in two ways. That is a heterolytic cleavage or a homolytic cleavage. Heterolytic cleavage, it is referred when a covalent bond it is broken in such a way that both the pair of electrons that are taken by the one fragment itself. Suppose we are having a bond between A and B. If there is heterolysis, that is cleavage of bond in such a way that both the pair of electrons is taken by one fragment, then what will happen? Here we will get A plus and B minus, or B plus and A minus. Okay. So it means what? Both the electrons of this pair which is present in this bond, that is taken by one atom. So earlier, since both the electrons were shared by the two atoms, and each atom had contributed one electron, now both the electron is taken by the one of the atoms. So one of the atom is deficient of both the electrons. So there is a dissimilarity or in non-homogeneous distribution of electrons as compared to the original condition. So one will be a cation and one will be anion. So here we will get a cation and anion. If you go for the example, here we are having tertiary butyl chloride. So it will undergo a homolysis, heterolysis. It will undergo heterolysis. At that time, what is going to happen? We will get this tertiary butyl carbocation and Cl minus. Now, similarly, if there is a homolytic cleavage, it means what? The covalent bond, it is broken in such a way that each fragment, it takes up one of the bonding pair of electrons that was present in the bond. Okay. So if AB undergoes homolytic cleavage, then what will happen? Each of these atoms will take their share of electron. So both will be having one unpaired electron, and that is the formation of free radicals. So in case of the homolytic cleavage, we are getting, or homolysis, we are getting a pair of free radicals. But in case of heterolytic, we are getting ions. Okay. Now, the reaction, it cannot be only on the type of homolytic or heterolytic cleavage. Many times it happens that the chemistry is as such that the pair of electron, it is delocalized in a closed structure. That condition can also be that we are not going to get any intermediate in the form of ion or free radical. That happens when the migrating electrons are paired. Happens when migrating electrons are paired or unpaired. This type of reactions are called as the pericyclic reactions, where bond formation and bond breaking process, it takes in a cyclic manner, and it is a concerted reaction. Okay. And it is a continuous process. But our concern, it will be only with respect to homolytic and heterolytic cleavage in this unit. Now, if you go for the intermediates, as already we have seen, if there is a heterolytic cleavage, what we are going to get? We are going to get a carbocation for organic compound or carbanion. And if there is a heterolytic cleavage, in that case, we can get a free radical, and also we can get a carbon. Okay. Now, what are these intermediates actually? What is their structure? What is their reactivity? How they are formed? We will discuss in detail. If you go for carbocation, then in case of carbocations, they are having a positive charge, positively charged carbon atom, and it is formed when there is a heterolytic cleavage of the organic compound, which is having a covalent bond. So in this case, what is going to happen? The carbon that will be deficient of the shared pair of electron. So for that reason, it will carry a positive charge. So it has sp2 hybridization. Earlier, when it was bonded, all the atoms were having the shared pair of, all the bonded atoms were sharing a pair of electron. At that time, carbon was forming 4 bonds. It was having sp3 hybridization. So one of the bond is broken where the shared pair of electron is taken by the leaving group. At that time, what is going to happen? This is having a positive charge. What is the meaning of positive charge? It means absence of the electron, which it should retain with it. So what is going to happen? 3 sp2 orbitals are there, and the 4th orbital, that is vacant. Earlier we were having 4 sp3 orbitals. Now since one orbital is not having any electron, so hybridization, it changes to sp2. So the hybridization of carbocation, that is sp2 hybridization, in which there is a vacant p orbital, and it has a planar structure, and all these 3 bonds, they are at an angle of 120 degrees Celsius. 120 degrees, sorry, not Celsius. 120 degrees. So we are having a flat planar structure with 3 sigma bonds, and this is the orbital structure of sp2 hybrid. carbocation. Now, if you go for the stability, the order of stability of carbocations is shown as shown over here. The methyl carbocation, that is the least stable. The more stable is the ethyl carbocation because of increased plus I effect of this CH3 group. The next is isopropyl carbocation. Because isopropyl carbocation, it is having two methyl groups attached to it as compared to ethyl carbocation, which has only one CH3 group attached to it. The more stable is allylic carbocation, because in case of allyl carbocation, you can have two resonating structures. Okay. This plus charge on this carbon atom, it can migrate to this one, and these two carbon atoms can have double bond. And more stable is benzyl carbocation, where this positive charge, it can be delocalized in this phenyl ring. And more stable than benzyl carbocation is the tertiary butyl carbocation. In case of tertiary butyl carbocations, we are having 3 methyl group which are going to have plus I, which are having plus I effect. And more stable than this tertiary butyl carbocation is diphenyl methyl carbocation, where we are having 2 phenyl groups. So the delocalization of this positive charge, it can occur in 2 phenyl groups. So it can have more resonating structures. And more is the number of resonating structures possible, more is the stability as per the rules of the resonance. Similarly, in case of this triphenyl methyl carbocation, the stability is still higher. And the most stable among these is the cycloheptatrinyl cation. In this case, it is a 7-member ring having 3 triple bonds. And these 3 triple bonds, they are delocalized because of presence of an excess positive charge upon the carbon atom. So that causes the delocalization, and we can write more resonating structure for this compound as compared to phenyl carbocation or benzyl. Now, if we go for only this alkyl carbocations, then clearly the primary one is the least stable, more stable is the secondary one, and highest stable is the tertiary carbocation. The reason is same in case of as we move from primary to secondary to tertiary, the number of methyl groups that is attached to the positively charged carbon atom, it increases. So for that reason, plus I effect, it is increasing, and which causes the increase in the electron density on the carbon atom bearing positive charge. So for that reason, the stability in it is highest for tertiary carbocation and least for primary carbocation. And also hyperconjugation is also responsible, which causes the increase in stability of tertiary carbocation and least for the primary carbocation. If in terms of data you want to see, then as compared to methyl carbocation, if you go for tertiary butyl carbocation, the stability is, additional stability is there for 84 kilocalorie per mole. Yeah. From structure also you can see in case of primary carbocation, we are having only 1 methyl group attached. In case of secondary, we are having 2 methyl groups or alkyl groups attached to the carbocation. In case of tertiary, we are having 3 alkyl groups attached to the carbocation. So it causes maximum neutralization of the positive charge on this electron deficient carbon. Now, if we go for the generation, this was all about the stability. If you go for generation, then they can be, that is the carbocations can be generated by several pathways. One is the direct ionization, electrolytic cleavage of the CX bond. Okay. And second is by the protonation of alkene by carbonyl compounds, alkenes and carbonyl compounds. So here we are protonating this carbonyl compound. In this case, this H plus, it will be attached to this oxygen. We will be having this hydroxyl group, and this positive charge on oxygen atom that can resonate, it can be shifted towards this carbon atom, and we can get a carbocation. If we go for protonation of alcohols, in that case also, this hydroproton, it can be taken up by hydroxyl group, and water molecule, it can be easily released. So what will happen? This positive charge, it will be on this alkyl group. So we can get a carbocations. Deamination of amines and nitrous acid, that can also result in the release of nitrogen at nitrogen molecule. So what will have, what is going to happen? We can get a carbocation. Now, if we want to see the reactions of carbocations, in that case, if they can, this carbocations, they are the electron deficient species. Now, since they are electron deficient species, so they can easily combine with the nucleophiles. They themselves are electrophiles. They are electron deficient, so they are basically electrophile. So they can easily combine with nucleophiles, such as in the first case, we can see hydroxyl group, it can easily get attached to this tertiary butyl carbocation, and we can get an alcohol. If we go for elimination reaction, that can also happen by elimination of H plus ion. We can get formation of, we can see the formation of alkene. Then this hydrogen atom, it can migrate in case of carbocations if it is a primary carbocation or secondary carbocation, because we know it very well that primary is the least stable. So whenever we are having a primary carbocation, it has chance to form or get converted to secondary or tertiary. It will prefer for it. So we can have a rearrangement reactions in case of primary or the secondary carbocations, so that we can get a relatively a more stable carbocation. So the arrangement reactions are possible. Now, if we go for this carbanions, in case of carbanions, that is the heterolytic cleavage in which the shared pair of atom that is retained by the carbon atom. So we can see, we can get a methyl carbanion, then we can have ethyl carbanion, then isopropyl carbanion, tertiary butyl carbanion. Now, in case of carbanion, the shared pair of electron is retained by the carbon atom. So for that reason, there is not any appearance of vacant p orbital. sp3 hybrid, 4 sp3 hybrid orbitals are there. Initially, 4 single bonds are formed by this carbon atoms. Now, this fourth bond, when it is broken, the shared pair of the electrons is retained by the sp3 hybrid orbital. So the geometry, it is retained because of the retention of the hybridization. We are having 4 sp3 hybrid orbitals. 3 will be forming sigma bond, and fourth one, that will be the non-bonding orbital with 2 pair of electrons. If we try to check for the stability, now in this case, they are the negatively charged species. So if there is plus I effect, that will decrease its stability. So the order of stability is reversed in this case. Methyl carbanion, that is the most stable, and the tertiary carbanion, it is the least stable, because it is already a negatively charged species to which we have attached the plus I effect contributing substituents that is going to further increase the electron density at the carbon atom. So for that reason, it decreases its stability. If we try to look from the point of view of resonance, then if this carbanion, it is attached to phenyl group, then the stability, it increases. Why it increases? Because of this resonance, this negative charge, it is distributed among 4 resonating structures. In case of allylic carbanion, the stability is higher as compared to your tertiary carbanion, because in this case, we are having the chances for formation of more resonating structure. So for that reason, this allylic and benzylic or other aromatic carbanions, they are relatively more stable. Now, if we try to see for the resonance of plus I effect, when this carbanion, it is conjugated with a carbon oxygen and carbon nitrogen multiple bonds. In that case, the stability of the carbanion is greater as compared to this benzyl or the allylic carbon, because this nitrogen or oxygen, these atoms are electronegative, so they tend to reduce the electron density on carbon atoms. So for that reason, for the reason of being more electronegative than carbon, they stabilize the carbanion. And these electronegative atoms are having better capability for bearing the negative charge as compared to the carbon atom, because electronegativity of nitrogen and oxygen is far higher as compared to the carbon. Now, if we try to understand in terms of stability, if there is formation of double bond or triple bond, then it is found that this carbanion, it is more stable if it is having multiple bonds. That is hybridization, it is sp, then it is more stable. Lesser is in case of sp2 and less is in case of sp3. Why? Because as hybridization, it moves from sp to sp3, the s character, it decreases. So lesser the s character, more is the instability of the carbanion. So for that reason, we can see this triple bonded carbanion that is most stable because of higher s character, because there is one s orbital and one p orbital. So for that reason, it is then 50% s characters, and s orbital is more located towards the nucleus. So for that reason, it is more electron withdrawing with respect to the sp2 or sp3 hybrid orbitals. So increase in the s character means the electrons are closer to the nucleus and they are having lower energy. So for which they are more stable. If we try to see the reactions of the carbanions, then most common reaction of carbanions is the combination with the positive charge. So they are negatively charged species, so they will combine with the positively charged species, that is the electrophiles. Okay. So they can easily combine with the protons or the positively charged species. In this case, we can see that this we are having this methyl carbanion, it can easily react with this HX and it will form the methane. Now carbanions, they frequently add to carbonyl group or carbonyl double bond, which is observed in case of aldol condensation. Now if you go for free radicals, in case of free radicals, free radicals, they are formed by the homolytic cleavage. So in this case, the species has one unpaired electron, and here the structure that is possible in both ways, sp2 or sp3. Similar to carbanions, the carbon containing unpaired electron in free radicals can be in sp2 hybrid state, for which the structure it will be planar with odd electrons in the p orbital. It can be sp3 hybrid orbital where the structure that is pyramidal, as in case of our this carbanion. Here the unpaired electron that will be in the fourth sp3 hybrid orbital. So it can have sp3 or sp2 hybrid structures both. It can be planar or it can be pyramidal. Now this the physical and chemical evidences for this structure that can be that has been obtained from ESR spectroscopy. The planar configuration at the radical center for simple alkyl radicals, but for fluorinated derivatives, it is found to prefer the pyramidal structure. The resonance stabilized free radical and the radical carbon is certainly in sp2 hybrid state. Now, if we try to look for how these species are formed, in the formation of these radicals that can take by the thermal cleavage or the photolytic cleavage, but one of the necessary conditions is that there should be such forms present in the substrate which can undergo homolytic cleavage, which is easily found in case where in those cases where there are either compounds or the peroxylated compound, that is the linkages between oxygen and oxygen single bond. Okay. So in those cases, the thermal treatment that causes the homolytic cleavage, and these are the designated as the initiators, this peroxide compound or the other compounds. So they readily undergo homolytic cleavage to form the free radicals. The photochemical cleavage can also occur where there is the there is a great chance of getting a radical through irradiation of the light upon the substrate, where the energy is transferred to the molecule by the interaction that must be of the order of the bond fission energy to cause the homolysis. So we can get this RCO dot and R dot by the homolytic cleavages of this ketonic compound. Okay. Now, this in case of halogens, they readily undergo homolytic cleavage, so they can form the radicals which can undergo reactions to cause the generation of carbon-free radicals, such as we can see in case of chemical methods. This CCl bond, it can also undergo cleavage in presence of silver because it is a very photoactive. So it will cause the formation of AgCl, and which is a very stable precipitate, and it will result in the formation of this carbon-free radical. Through redox reactions, we can also have the formation of radicals in the cases where we are having this azo group present, N2 group is present, nitrogen atom can be easily released in these structures, and we can have the formation of this phenyl radical. If we try to look for the stability, then stability of free radicals, if we want to look for, then in this case also the stability, it follows the same order as we have seen in case of the carbanion. That methyl is the less stable, more stable is the primary free radical, then secondary free radical, then the tertiary free radical. So in this case also we can get to see that that stability, it decreases as we move from tertiary to secondary to primary and methyl free radicals. The stability of the free radicals that can be explained on the basis of hyperconjugations. The sigma electrons of the CH alpha CH bond can delocalize with the half-filled p orbital of the carbon atom containing odd electrons, thus spreading the odd electron all over such bonds, and thereby stabilizing the radical. So for which as the number of alkyl group it increases, more is the stability of this carbon-free radicals, which follow the same trend as we have seen in case of our carbocation. Okay. Now, the reaction of free radicals, they can undergo halogenation. They can cause halogenation of this alkenes, because this CCXX or this halogen molecules, they can undergo homolytic cleavage very readily, and when they are combining with alkanes, they can form HX, and the carbon-free radical is generated. And similarly, it can be result in the formation of generation of free radicals if the alkenes, they are allowed to react with HBr, because this HBr, it readily undergoes homolytic cleavage in presence of light. So Br dot that is formed, and it results in the cleavage of this double bond and causes the formation of the carbon-free radical. Now that can neutralize itself by two ways, either combination of two free radicals or by disproportionation, where the double bond is formed between these two species which are attached to these free radicals, and others, these two CH3 groups, they are going to attach by the single bond. So with this, we stop in today's class. In the next class, we will discuss about the nucleophilic reactions and also about the transition state. So first we will discuss about the transition state theory and the terms related to the free energy, and thereafter free energy or the rate of reaction and energy profile diagram also, and thereafter we will discuss about substitution nucleophilic reactions. Thank you.